Spark Shuffle is the process of moving data across partitions so records with the same key can end up together. Before the shuffle, data is usually distributed based on the original input partitions. That means records with the same key may be located in different executors. This distribution happens automatically when data is read from sources like files or databases, and it's the default way Spark handles data initially. However, this setup can lead to situations where related data isn't grouped together, making certain operations less efficient. During the shuffle, Spark transfers data across the network. This is where the data is reorganized and routed to the correct reduce side partition. The process involves moving data from one node to another, which is necessary when you need to aggregate or combine data based on specific keys. This step ensures that all records with the same key end up in the same place, allowing for more effective processing downstream. After the shuffle, the data is grouped by key. For example, all blue records go to one reduce partition, all green records go to another, and so on. This grouping is essential for operations like aggregations or joins, where you need to bring together all related data. It makes it easier for Spark to process large volumes of information efficiently, as each partition can be handled independently. This process is used by wide transformations such as join, groupByKey, reduceByKey, repartition, and distinct. These operations require data to be moved across the cluster, which is why they are considered wide transformations. They often involve significant overhead, especially when dealing with large data sets, because of the need to transfer and reorganize data. The important idea is this: Shuffle is powerful because it allows Spark to regroup distributed data, but it is also expensive because it uses network transfer, disk I/O, memory, and CPU. Every time a shuffle occurs, resources are consumed, and this can slow down overall performance if not managed carefully. Understanding when and how shuffles happen is crucial for optimizing Spark applications. It also creates a stage boundary. That means Spark finishes the map side work first, writes intermediate shuffle data, and then starts a new reduce side stage. This division into stages helps Spark manage execution flow and ensure that data is properly prepared before moving on to the next phase of processing. So, whenever Spark needs records from many partitions to produce one output partition, a shuffle is required. This is a fundamental part of how Spark handles complex data transformations, and it plays a key role in determining the efficiency and scalability of your applications. Being aware of shuffle behavior can help you make better decisions about data partitioning and transformation strategies. Shuffle happens during wide transformations, not narrow transformations. In a narrow transformation, each output partition is generated based on data from a single parent partition or a limited number of nearby parent partitions. This means that the processing for each output partition can be done without moving much data across the cluster. Such transformations are efficient because they minimize data movement and keep computations localized. Examples of narrow transformations include operations like map, filter, and union, where the data doesn't need to be reorganized across different partitions. Another example is a join between two datasets that are already co-partitioned, meaning their data is organized in a way that makes the join process straightforward and efficient. Because of this local nature, Spark can handle these transformations within the same stage. There's no need to move data between different nodes, which helps maintain performance and reduces overhead. On the other hand, wide transformations involve data from multiple partitions, which often requires more complex processing. These transformations typically require a shuffle, where data is redistributed across the cluster to ensure that related records are grouped together. Operations such as groupByKey, reduceByKey, distinct, repartition, and joins with non-co-partitioned datasets usually fall into this category. For instance, with groupByKey, all records sharing the same key must be gathered in one place to be processed together. Since these keys can be spread out across the entire cluster, Spark has to transfer data between executors. This data movement introduces additional steps and creates a new stage in the execution plan. As a result, the job becomes more resource-intensive and may take longer to complete. The general rule is simple. If an output partition needs to collect data from many input partitions, a shuffle is necessary. This distinction between narrow and wide transformations is crucial for understanding how Spark processes data efficiently and optimizes job execution. The first major part of Shuffle is called Shuffle Write. This process takes place on the map side, and it is a crucial step that must be completed before any reduce side tasks can begin. Without proper shuffle right, the data needed for reducing cannot be properly organized or accessed. First, each map task reads and processes its input partition. This means that the data assigned to a specific map task is loaded into memory, and the task begins processing it according to the logic defined in the application. Once this is done, the next step in the shuffle process begins. Then, Spark determines where each record should go based on the target reduce partition. This decision is usually made by looking at the key of the data and using the partitioner specified in the application. The partitioner helps distribute the data evenly across the reduced tasks, ensuring that all records with the same key end up in the same reduce partition. Next, the records are grouped into buckets. Each bucket corresponds to one target reduce partition. This grouping ensures that all data destined for a particular reduce task is collected together, making it easier to handle during the next steps. After that, Spark sorts and serializes the data. Sorting is important because it ensures that the data is in the correct order for the reduce phase. Serialization, on the other hand, converts the records into a format that can be efficiently written to disk and transferred over the network later. This step is essential for optimizing both storage and data transfer. Finally, the shuffle files are written to the local disk of the executor. These files act as temporary storage for the intermediate data generated by the map tasks. They remain there until the reduce tasks need them, at which point they will be fetched and processed. This is an important point. Shuffle write does not immediately send all the data to the reduce tasks. Instead, it prepares these intermediate files, which the reduce tasks will later retrieve from the disk. This approach helps manage large volumes of data more efficiently and prevents the system from becoming overwhelmed. If the data being processed is very large, Spark may spill some of it to disk while processing. This happens when the data exceeds the available memory, and it can increase disk I/O, potentially slowing down the overall job. However, this mechanism is necessary to ensure that even large datasets can be handled effectively. In summary, shuffle write is the preparation phase where map tasks organize, sort, serialize, and write intermediate shuffle data. It plays a critical role in ensuring that the data is ready for the reduce phase, enabling efficient and scalable data processing in distributed systems. The second major part of shuffle is called shuffle read. This process takes place on the reduce side once the shuffle files have been successfully written by the map tasks. During this phase, each reduce task must retrieve the data blocks that correspond to its specific output partition. These blocks can be stored on multiple executors across the cluster since the original data was distributed throughout the system. As a result, reduce tasks need to fetch these blocks over the network, which involves transferring large amounts of data between different nodes. Once the blocks are received, Spark merges and sorts the data based on the key. This ensures that all records with the same key are grouped together within the same reduce task, making it easier to perform further operations. At this stage, Spark is ready to carry out actions such as aggregation, joining datasets, or applying additional transformations. Shuffle read is often considered a costly operation because each reduce task may have to access data from numerous executors, leading to significant network traffic and increased memory usage. The main concept behind shuffle read is that it initiates a new processing stage, allowing Spark to work with the grouped data required for key-based operations. Shuffle is one of the most expensive operations in Spark. This is because it involves a series of complex processes that can significantly impact performance and resource usage. The first reason is network transfer. When data needs to be shuffled, it often moves between executors, which may be located on different machines within the cluster. This movement requires transferring large volumes of data across the network, which can be slow and consume significant bandwidth. The second reason is disk I/O. During shuffle write, Spark writes intermediate data to disk. This step is essential for managing large datasets that cannot fit entirely in memory. However, when this data needs to be read back during the shuffle read phase, it again requires accessing the disk, which can introduce delays and increase I/O load. The third reason is serialization. To efficiently store and transfer data, Spark must encode and decode objects. This process, while necessary, adds overhead and can slow down the overall execution time. The fourth reason is data skew. If one key has much more data than the others, one reduce task can end up receiving a huge amount of data while other tasks finish quickly. This imbalance can cause certain tasks to take much longer than others, creating what are known as stragglers. These slow tasks can delay the entire stage and affect the overall performance of the job. All of these costs can lead to longer stage times, higher memory pressure, more disk spills, retries, and sometimes job failures. It's important to understand that while shuffle is necessary in many cases, it should never be done without a clear purpose. Every shuffle should be intentional, as it can have a major impact on the efficiency and reliability of Spark applications. Therefore, minimizing unnecessary shuffles is one of the most important skills for building efficient Spark applications. When aggregating data by key, reduceByKey is usually much more efficient than groupByKey. This is because groupByKey requires Spark to transfer all values associated with each key across the network to a single reducer, which can be very costly in terms of both time and resources. For example, if a particular key appears in many partitions, all the raw values for that key are first collected and then sent to the reducer. This process can create a significant amount of network traffic and put a heavy load on memory, especially when certain keys have a large number of associated values. In contrast, reduceByKey performs local aggregation before the shuffle. This means that each mapper combines the values with the same key locally on its own node before sending any data over the network. As a result, only the intermediate results are transferred rather than the entire set of raw values. For instance, instead of sending multiple individual values for a key like key 1, each mapper sends just one combined value for that key. This approach significantly reduces the amount of data that needs to be shuffled across the cluster, leading to better overall performance. The recommendation is straightforward. Use reduceByKey whenever you're performing an aggregation operation. Only use groupByKey if you absolutely need access to all the original values for a given key, as it is generally less efficient and should be used sparingly. There are several ways to reduce shuffle cost in Spark. When working with large-scale data processing, minimizing the amount of data that needs to be shuffled across the cluster can significantly improve performance and resource efficiency. Understanding and implementing effective strategies is essential for optimizing Spark jobs. The first strategy is using a broadcast join. If one table is small enough, Spark can send that small table to all executors. This approach allows each executor to have a complete copy of the smaller dataset, which makes it possible to perform joins locally without needing to move large amounts of data between nodes. This not only reduces shuffle operations but also speeds up the overall execution time. Then each executor can join locally with its own partitions, avoiding a large shuffle. By keeping the smaller dataset close to where the data is processed, the system avoids the overhead associated with redistributing data across the network. This is especially useful when dealing with scenarios where one dataset is much smaller than the other, making it feasible to broadcast it efficiently. The second strategy is smart partitioning. If two datasets are partitioned by the same key and use compatible partitioning, Spark can keep related records together. This means that during operations like joins or aggregations, the data required for each operation is already grouped in a way that minimizes movement. This helps avoid unnecessary data movement during joins or aggregations, leading to faster execution and lower resource consumption. The third strategy is to repartition wisely. Repartitioning is a powerful tool that allows you to change the data layout or increase parallelism, but it triggers a full shuffle. This means that all the data must be redistributed across the cluster, which can be costly in terms of time and resources. It's important to consider whether this step is truly necessary before deciding to use it. Repartition can be useful when you need to change the data layout or increase parallelism, but it triggers a full shuffle. If you only need to reduce the number of partitions, coalesce is often cheaper because it can merge existing partitions with less data movement. Coalescing is a more efficient alternative when the goal is simply to decrease the number of partitions rather than redistribute them entirely. The main lesson is, choose your partitioning strategy carefully. The right choice depends on the specific characteristics of your data and the operations you're performing. A well-thought-out plan can save significant time and resources in the long run. The best shuffle is the one you never have to do. By designing your data processing workflows with efficiency in mind, you can minimize the need for expensive shuffle operations and make your Spark applications run smoother and faster. Inside Spark, Shuffle is managed by specialized components that play a crucial role in the execution of distributed data processing tasks. These components ensure that data is efficiently moved and organized across different stages of a job. On the map side, Spark uses the Shuffle Manager to organize and write shuffle data. This process is essential for preparing data to be consumed by subsequent tasks. The default manager is commonly known as the Sort Shuffle Manager. It works by sorting the data, organizing it by target partition, and reducing file overhead. This helps in making the data more structured and easier to handle during the next phase. The output of this phase is a set of shuffle files or shuffle blocks stored on local disk. These files contain the intermediate results that will be used by the reduced tasks. By storing them locally, Spark minimizes the need for repeated data transfers and improves overall performance. On the reduce side, Spark uses a shuffle reader to fetch the blocks needed by each reduce task. This component is responsible for retrieving the correct shuffle blocks from different executors and bringing them to the reduce task. The block shuffle reader plays a key role in this process, ensuring that the right data is available at the right time. Once the data is retrieved, Spark can merge the data and continue processing. This merging step is important for combining results from different partitions and preparing the final output. From a performance perspective, the best practices are clear. Minimize wide transformations when possible, as they can lead to increased data shuffling and resource usage. Watch for data skew, which can cause some tasks to take much longer than others. Prefer reduceByKey over groupByKey for aggregations, as it is more efficient and reduces the amount of data shuffled. Broadcast small tables when appropriate, as it can significantly improve join operations. And choose your number of partitions carefully, as it affects how data is distributed and processed. Understanding these components helps you reason about where time, memory, network, and disk usage are being spent during a Spark job. This knowledge allows you to optimize your code, identify bottlenecks, and make informed decisions to improve the efficiency and scalability of your applications.